Hello dear students, let's have a journey on system of nonlinear equations and we try to solve these equations using Newton Raphson method. Now we extend our previous methods. We have learned several numerical methods for finding roots. Newton Raphson method, fixed point iteration, regular falsy method, bisection method, graphical, tabulation, secant method, lot of that. So that is for linear equations only. Single equation fx equal to 0. But we might have nonlinear equations also. We might have two equations or maybe n number of equations. So we can generalize this method. So this video will be very helpful for you in future aspects. So we first consider system of two nonlinear equations in two unknowns, fxy equal to 0 and gxy equal to 0. Function of xy, both are functions of xy, two nonlinear equations having, and two unknowns x and y. Now let xk yk be a suitable approximation to the root xi eta. So xi eta be the exact root of the system, above system, and let xk yk be a suitable approximation to the root, and let delta x be an increment in xk and delta y be an increment in yk, such that xk plus delta x comma yk plus delta y is the exact solution. Okay, so we can write the equation system, that is our system was from 1, we can write from 1 fxy equal to 0. So this equation becomes fxk plus delta x, yk plus delta y, that is I am replacing x by xk plus delta x, that is the approximation, and yk plus delta y, that is the approximation of y. So that is equivalent to 0. Similarly, we are replacing gxy in gxy x comma y by xk plus delta x and yk plus delta y. Okay, so we have this is equivalent to 0. Okay, now expanding in Taylor series about the point xk is yk, we get, you know that the Taylor series expansion fxk yk plus delta x del del x plus delta y del del y fxk yk plus 1 by factorial 2 delta x del del x plus delta y del del y whole square fxk yk, etc., and higher order partial differentiation. Okay, this is by Taylor series expansion. If you expand xk plus delta x, yk plus delta y by Taylor series, you will get this type of relations, this type of series. And similarly for g also, gxk yk plus delta x del del x, first order partial derivative delta y del del y, gxk yk, then is 1 by factorial 2 delta x del del x plus delta y del del y squared gxk yk plus etc., and so on, the higher order terms of the Taylor series. Now neglecting the higher order terms, because delta x and delta y are small, so we are neglecting second and higher order powers of delta x and delta y. We obtain simply fxk yk, you look at that, this one, and delta x del del x of fx is written as this del del x of fx comma y, this is written as fx, partial derivative with respect to x, right? This is written as partial derivative with respect to x, this x, and we can write partial derivative with respect to y as fy. This denotes partial derivative with respect to y. So you have this is the term if you neglect the second and higher order powers fxk yk. So this is equation 2, suppose, and delta x fx xk yk, delta y fy xk yk. So fx is the partial derivative with respect to x, fy is the partial derivative with respect to y, And similarly for g also, gx, gy, the partial derivatives with respect to x and y respectively. So this Taylor series neglecting higher powers reduced to equation 2. Now solving, we can solve these two equations simultaneously for delta x and delta y, right? You can get the value of delta x and delta y by solving simultaneously. You can solve it simultaneously. So you will get this type of relations. Minus 1 by dk delta x is given by f gy minus g fy, and delta y is given by minus 1 by dk g fx minus f gx, where dk is fx gy minus gx fy. Okay, so that you can easily check that this is the solution. So once you obtain the delta x, you can calculate xk plus 1, right? Look at that, you can calculate xk plus 1, that is equal to xk plus delta x. Similarly, you can calculate yk plus 1 equal to yk plus delta y. Let me repeat once again. If you can solve delta x and delta y from the above equations, you can get delta x is equal to minus 1 by dk this one, and delta y equal to minus 1 by dk this one. So dk is given by this. So once you have delta x and delta y, you can write xk plus 1 equal to xk plus delta x and yk plus 1 equal to yk plus delta y. Okay, so this is how you can express. Okay, yk plus 1 equal to yk plus delta y. So writing the equations, these equations, equation 2 actually. So writing these equations in matrix form, we can have, so I want to write this equation in matrix form. That is fx, the matrix is a 2 cross 2 matrix, fx fy gx gy at x comma xk yk, and the column matrix is delta x delta y. Okay, and you have minus another column matrix fg, and this matrix is denoted by jk. Okay, this is a very important expression, jk, where jk is the 2 cross 2 matrix, denotes the partial derivatives fx fy gx gy at xk comma yk, and delta bold x, that is the column matrix delta x delta y, and f bold f, that is the contain the functions, the column matrix having the functions fg at xk yk. Okay, so this is the matrix representation. This is 3. Now once you represent the matrix, you can get the inverse of jk, then you will get delta x. So the solution of the system 3 is delta x is equal to minus jk inverse, where jk inverse is given by inverse of this matrix, and that is you can calculate by 1 by dk gy minus fy minus gx fx at xk yk. So this is the inverse matrix of gk. Okay, so this is the inverse matrix. So once you know the inverse matrix, and that will be multiplied with f, matrix multiplication, you will get delta x. That's it, that's the method, very easy. Therefore we can write this one, and so xk plus 1 by yk plus 1, the column, it will be xk yk plus delta x delta y. You have calculated delta x delta y here, so you can write this. This is the solution where k equal to 0 1 2 etc, and this is the method. This is the method you can write, because your xk plus 1 is xk plus delta x, right? And yk plus 1 equal to yk plus delta y. Okay, so you have this expression number 4. This is the solution. This is the solution, and k is the iteration steps. This is the solution. This method given by 4 is an extension of the Newton Raphson method to a system of 2 cross 2 equations. So Newton Raphson method can be applied to nonlinear equations. This is the most important application, and for system of solutions also. System of nonlinear solutions. Nonlinear equations, finding the solutions. Okay. So let's have an example for that. Let's try with an example. I will explain an example for you. So you have an example. There are 2 equations, 1 two nonlinear equations. You see x square plus xy plus y square equal to 7 and x cube plus y cube equal to 9. So, and the initial point is given, x naught equal to 1.5, y naught is equal to 0.5. And the exact solution is also given, but here I have not written, not required. Okay, let me start with the solution. Okay, let me write, first of all, let me write the a function, the first function, that is x squared plus xy plus y squared minus 7, and gxy equal to x cube plus y cube minus 9. Okay, now let me write the JK matrix. What is your JK matrix? JK matrix is the partial differentiation, right, at xk yk. Partial differentiation, or fy, fx, fy, gx, gy. This matrix at xk yk, right? At xk yk. So that will be, if you differentiate partially, so this will be 2xk, first element, 2xk plus yk, and xk plus 2yk. And second row will be 3xk square, 3yk square, right? So this is the matrix. Okay, this is the matrix. So let me find out JK inverse. If once you get the matrix, you can find out JK inverse of this matrix. So the inverse of the matrix is 1 by dk, the determinant, okay, 3yk square. You can calculate that by adjoint and all that. I have calculated, so I am substituting the values. So 2yk and minus 3xk squared, 2xk yk plus yk. Okay, this is your inverse matrix, where dk, you can calculate the determinant of this matrix. So dk is you can calculate by modulus determinant of jk, right? You can calculate that. We now write the method. So you got inverse of the matrix. So let me write the method. The method is xk plus 1, yk plus 1, that is the approximation and iteration steps, equal to xk. This is the method already explained. You look at that. Yeah, this is the thing. Xk plus 1 is equal to xk minus jk inverse fxk, right? And xk is this matrix actually. Okay, xk yk minus 1 by dk, that matrix 3yk squared minus xk plus 2yk. Okay, you look at that, this one, and this is your minus 3xk squared, 2xk plus yk. Okay, times multiplication. You look at the jk inverse into fk. You look at that, you have fk, fx, function at x1 y1, xk yk. So this is your function, x squared, x plus xy plus y square minus 7, and x cube plus y cube minus 9. So let me write that one. So it will be xk squared plus xk yk plus yk squared minus 7, and this one is xk squared plus yk squared minus 9. Okay, this is complete. This is the matrix. So this is the method. Okay, now use your x naught y naught is given, the initial approximation is given 1.5 and 0.5. You substitute for k equal to 0, 1, 2, etc. Now we'll use k equal to 0, 1, 2, etc. Let us have 1 or 2 expression. Let me show you one approximation. That will be better. So if you substitute k equal to 0, this column will be x equal to 1, x1. So x1, y1, right, equal to, this will be xk will be x naught, y naught. So that will be 1.5, 0.5. Okay, minus, you can calculate dk. Dk is x naught, y naught. What is your dk? Dk is determinant of this. So what is your jk? Jk is this one. So this is x naught, y naught, x naught, 3x naught square, x naught, 2y naught, 3y naught square. So you can substitute the values 1.5, 0.5. So you can calculate minus 14.25. I have calculated, so I'm giving you the value. You can verify that by 1 over, and this is the matrix, inverse matrix, 3yk square. So y naught square minus x naught plus 2y naught. Second row, minus 3x naught square plus 2x naught plus y naught. So that will be 0.75. I have calculated, so I'm giving you the data. The data is with me. Minus 2.5, minus 6.75, and 3.5. This is the inverse matrix. And finally the function value. Functional value will be x naught square. This is your functional value. X naught square plus x naught y naught plus y naught square minus 7. And x naught square plus y naught square minus 9. So this will be calculated like this. Minus 3.75. This column matrix minus 5.50. Okay. So ultimately you have, after calculation, 2.2675 and 0.9254. That's it. So you have x1, y1. You have now x1, y1. So next iteration is x2, y2. So this one is required for that. So next you will substitute this one, right? So next iteration, your x1, y1 is replaced by next iteration is this one. So 2.2675, 0.9254, and so on. You can do the same process. You can calculate dk for now your x1, y1. Everything will be x1, y1. So this is your x1, y1 minus 1 by dk. Dk will be in terms of x1, y1. And this inverse matrix will be in terms of x1, y1. And the functional values will be in terms of x1, y1. Then you will get x2, y2. Again, at the last, you have to calculate x3, y3 using that x2, y2. So that is your approximation. Maybe 3 approximation or 4 approximations are required. So this is how you can apply your method. That is the Newton Raphson method in nonlinear equations also. This is for nonlinear solving. This is how you can solve nonlinear equations. So, and this method can be generalized to several n equations also. So that is, in that case, your n dimensional matrix, n cross n matrix or inverse matrix, you can calculate. So this is how you can have a general computer programming for that also. Okay. Now, next one is how to deal with the problems of complex roots or complex equations. So this method can be, we can generalize this method for complex, finding the complex solutions, okay, for an equations fz equal to 0. Fz equal to 0 is a complex equation. So we have to find out the roots of this equation, okay. So in that case, suppose z equal to x plus iy, okay. Z is your x plus iy. So if z is, suppose f of x plus iy, right? And that is equal to uxy, that is a real part, and ivxy, that is an imaginary part. Ux and vxy both are functions of x and y, and that is equal to 0, and both are real number. So you have two systems actually, uxy equal to 0 and vxy equal to 0. Okay, so look at that, these are two equations of two unknowns x and y, and these are nonlinear equations. This may be nonlinear, maybe linear, but system of equations you have. So you can use your previous method to solve these equations. So complex roots, also you can find out the complex roots of a system of equations, or complex, okay, methods for complex roots. That is why this is. So let's have an example for that. Obtain the complex roots of the equation z cube plus 1 equal to 0 using the initial approximation of the roots 0.25 and 0.25. Okay, so let z equal to x plus iy. I'm just giving you a hint. The equations, I will just generate the equations. So your f of x plus iy would be x plus iy whole cube plus 1. So that is equal to, if you simplify, the real part will be x cube minus 3xy square plus 1 plus I into 3x squared y square x square y minus y cube equal to 0. So you have two systems. One is uxy equal to x cube minus 3xy square plus 1 equal to 0. Another one is vxy equal to 3x squared y minus y cube equal to 0. That's it. That's it. So you can write the j, the matrix for partial derivatives, ux, uy, vx, vy. So you have 3x squared minus 3y squared minus 6xy, 6xy, 3x squared minus 3y squared. Okay, and what is the determinant? You can calculate the determinant. That is equal to, you can calculate 9x squared plus y squared whole squared. Okay, and you can calculate the inverse matrix. J inverse is 1 by d 3x squared. You can verify this, please calculate by yourself. This is already calculated. Minus 6xy 3x squared minus y squared. This is the inverse matrix. So now you can apply your method. The method is xk plus 1, yk plus 1 equal to xk yk. That is the initial approximation is given here. So look at that initial approximation, 0.25, 0.25. So your, instead of this you have 0.25, 0.25 minus 1 by dk. You will substitute, you will calculate the values, and these values will be in terms of this matrix. I'm not writing this. And the lastly the function itself, that is uxy vxy. Just similarly you can calculate the root by initial approximation, that is x1 y1. You can calculate that, and that will be, you can check. I'm giving you the answer for checking. Please calculate. This is your assignment. You can do that. 1.66666667, and this one will be 2.8333333. Okay, please verify this one. This is the answer. If you want second approximation, you can do that using this as the approximation. So on. So this is how you can deal with the complex roots, and also for system of equations. Okay, so this is my lecture today. So I'll stop here. Please follow my videos, subscribe my channel, share with your friends, and put some comments. Thank you, all of you.